Hello everyone, welcome to another daily math puzzle. I'm going to start by giving you the solutions for the last puzzle I posed, and then we're going to have a new one, and I think you'll like it today. So, last puzzle was that we had the equation n to the power of 4 plus 2n cubed plus 2n squared plus 2n plus 1, where n is a positive integer, and we had to show that that equation never gives a perfect square, so that equation is never equal to an integer squared. So if you want to pause the video and think about that for a while, go ahead, because now I'm going to reveal solutions. I've actually got a couple of solutions today. There's a couple of nice ways to do it. It helps if it's the right way around. And here we are. So this is probably the most elegant solution that I know of. Let's call our quantity Q. So Q is n to the power of 4 plus 2n cubed plus 2n squared plus 2n plus 1. And we want to show that Q is not a perfect square. So how do we do it? Well, we can do it with inequalities. So we can see that n squared plus n, all squared, is always less than Q. And we can see that n squared plus n plus 1, all squared, is always greater than Q. So since these two things here are consecutive perfect squares, and Q lies between them, that means that Q can't be a perfect square. So that's one way. This is the other way, which I found a bit faster. We can factorise Q, and we can write it as n squared plus 1 times n plus 1 times n plus 1. And so let's do a proof by contradiction. We're going to suppose that this thing is a perfect square, and then we'll derive a contradiction. So we'll suppose that this is equal to k squared for some positive integer k. Now, looking at this factorisation, we can take this equation and we can see that k squared divided by n plus 1 squared is equal to n squared plus 1. Well, this is a square, a perfect square divided by a perfect square. And if you think about it, whenever a perfect square divides by another perfect square and gives an integer answer, that integer has to also be a perfect square. You can see that by thinking of the prime factorizations of the different numbers involved. So that means that n plus 1 itself has, n squared plus 1, has to be a perfect square. So we can write n squared plus 1 equals m squared. And now we find our contradiction, because this equation shows us that something's wrong, because we've got positive integers n and m such that n squared plus 1 equals m squared. Well, that simply doesn't happen for positive integers, because if you think about all of the squares of positive integers, you've got 1, 4, 9, 16 and so on, and each of those is separated by a gap of more than 1. So we're never going to have a couple of perfect squares separated by a gap of 1. So this is a contradiction, which must have meant that this initial assumption was wrong. So yeah, that's a couple of proofs of those. Hope you enjoyed that one. Diaphanting equations are always fun, or totally impossible. Okay, so this is the next puzzle. This is a rather nice one. The answer is there, so short, if you know it. So the idea is that we have an ellipse, and it's not a circular ellipse. It's a sort of irregular ellipse, if you like, where it's stretched out further one way than in the other way. And we want to show that it's impossible to inscribe a regular n-gon on this ellipse so that the vertices of the n-gon are drawn on the ellipse when n is bigger than 4. So as is shown very roughly here, if you have a square, you can draw a square so that all of its vertices are on the ellipse. But if you have a pentagon or a regular pentagon or a regular hexagon and so on, then the problem can no longer be solved. It's not possible to inscribe such a regular n-gon on such a irregular ellipse. And so the question is, how do you show it? And I want to tell you a sort of hint, a fact that you can assume to show this in a very, very short manner. If you should probably already know this fact, but since I don't think you have to prove it to solve this problem, I'll tell you it so you can assume it. If you want to stop the video now and make it a proper challenge, go ahead, because this fact will probably get you to the answer here much, much faster. So the important fact is that every circle and every ellipse, if you have a circle and you have an ellipse, then they're not going to intersect at more than 4 points. So good luck with this problem.